Bismillahirrahmanirrahim. We are just starting it because there are few foreigners also participating in the talk. So we will discuss it in English, and in the end you can ask your question, and we will try to answer all that sort of the things. My company name is United Engineering Services. We are a consulting firm doing some sort of consultancy service in industrial sector, and established in 2001. And we have a very experienced. I have worked. I have an experience of. My name is Tahir Saleem, having an experience of 45 to 50 years, and no more normally in the industrial sector, and we try to do our best in industrial sector because there is a lot of lack of knowledge in engineers in this subject. So this fault analysis is very important as far as the short circuit currents is concerned. This is very critical, and a lot of damage you can save in applying this technique. If you have the correct parameter, it will help you to select your components according to your protection system. So for electrical safety, this is a very important. A lot of fire and occur because of the lack of non-technical staff selecting electrical components not as per fault analysis resulted in fire hazards, and a lot of damage, fatal accidents occurs because of this. If you select the correct component according to your protection system, what is the fault, what is the fault level, what is the fault zone at your section, then you will be safe enough and your power will be out. Please remember it. Electrical safety depends upon only your power off. So your safety is to be considered because the immediate tripping of the system for LT as per IC code for LT 400 volt system, the maximum tripping time is 0.07 second, a three phase system, 0.07 second. So you have to take into consideration all these sort of the things. People selected as abruptly, and there are two things in this: Ku and Ks. Ku is the ultimate capacity in which we can sustain your fault current maximum at this level, and there is the Ks factor for which you have to select the setting of the Ks according to your requirement, at what level of fault level location, at what location, what is the system capacity. You have to adjust your Ks values accordingly, and so that it can magnetic tripping of the breaker or fuse may trip accordingly in the minimum possible time, and you will not have any damage. So let's come to the presentation first, and we will start our presentation and start. And you have to know how to calculate all these things. In fact, the fault calculation will be considered very important for the component selection and electrical safety. It's a very important. But in the end, we will do the fault calculation by using the ETAP software. Now you will have a know-how about that. So the manually it is a little difficult, but I will try my best to minimize the complete complex equations, and we'll give you some solution for that. There are many methods on that. So let's go forward and see what is there. The first is introduction. All electrical network machines and equipments are often subject to various types of faults while they are in operation. When a fault occurs, the characteristic values such as impedance of the machines may change from existing value to different values till the fault is clear. All depends upon the impedance, the total impedance. So if the fault occurs, the impedance reaches to zero or a minimum value because the load is short circuited to the ground, you will have a phase to ground or phase to phase fault. So that the current will increase as per Ohm's law, and you have to select your component accordingly at that level. So first of all, there is very important, the location of the fault is very important. So you have to take into consideration impedance. You have to calculate the impedance up to the fault level and then calculate your short circuit current. And the third step would be that you have to select your component according to Ku and Ks. Ks is the system capacity and Ku will be your ultimate capacity. There may be a lot of probabilities of faults to appear in the power system network, including lighting, wind, tree falling in lines, apparatus failure, whatever it may be. A fault in an electric power system can be defined as any abnormal condition. When the fault occurs, abnormal conditions exist that involve the electrical failure of the equipment such as transformer, generator, bus bar, etc. and the fire can result. The fault detection also involves the insulation failure and conducting path failure, which results short circuit and open circuit of the conductors. Under normal or safe operating conditions, the electric equipment in a power system network operates at normal voltage and current ratings. So we are discussing actually LT network, not to the HT, because a lot of problem comes in the LT networks. So in Pakistan, we have a 415 volt three-phase voltage, and the electrical fault will be considered accordingly. Voltage and current values deviate from their normal range. The voltage will be zero if the fault occurs, and the current will be tremendously increased. It will be 10 to 12 times. The fault in a power system causes overcurrent, undervoltage, unbalance of the phases, reverse power, and high voltage surges. This results in interruption of the normal operation of the network, failure of the equipment, electrical fires, etc. Usually, power system networks are protected with switchgear protection equipment such as circuit breakers raised in order to limit the loss of the service due to electrical failure. The main thing is that how to select our protective system. Electrical faults in three-phase power system mainly classified into two types, namely open and short circuit faults. Further, these faults can be symmetrical or unsymmetrical faults. Let us discuss this fault in details. The first is that the open circuit fault, these faults occur due to the failure of the one or more conductors. The figure illustrates the open circuit fault for single, two, or three phases conductors open condition. The most common cause of these faults include joint failures of cables, overhead lines, and failure of one or more phases of the circuit breaker, and due to melting of the fuse or conductor in one or more phases. Open circuit faults are also called as series faults. These are unsymmetrical and unbalanced type of fault except three-phase open fault. Consider that the transmission line is working with a balanced load before the occurrence of the open circuit fault. If one of the phase gets melted, the actual loading of the alternator is reduced, and this causes to raise the acceleration of the alternator. The speed will increase. Thereby, it runs at a speed slightly greater than synchronous speed. This overspeed causes overvoltage in other transmission lines. This will be zero, and the second other two phases will be face to face. Thus, single and two-phase open circuit condition can produce the unbalance of the power system and current that causes great damage to the equipment. Broken conductor and malfunction of the circuit breaker affects abnormal operation of the system. You know, as an electrical engineer, exceeding the voltage beyond normal values in certain parts of the network, which further leads to insulation failure and developing of the short circuit. As per IEEE code, this exceeded voltage should not be more than 0.8 of your phase-to-phase voltage in earthing faults. So you have to be very careful about that, and you have to design your protection system accordingly with installing a breaker which will not allow our voltage more than 0.8 of the phase-to-phase voltage. Although open circuit faults can be tolerated for longer periods than short circuit faults, these must be removed as early as possible to reduce the greater damage. A short circuit can be defined as an abnormal connection of very low impedance between two points of different potential, whether made intentionally or accidentally. These are the most common and severe kind of faults, resulting in the flow of abnormal high current, which will be 10 to 12 times of your rated current through the equipment and transmission. If these errors can persist, even for a short period, it leads to the extensive damage to the equipment. Short circuit faults are also called as a shunt fault. These faults are caused due to the insulation failure between phase conductors or between earth and phase conductors. The various possible short circuit fault conditions include three-phase to earth, three-phase to earth, clear earth, phase to phase, single phase to earth, two phases to earth, and phase to phase plus single phase to earth, as shown in figure. You can see over here. This will be the bolted fault. We can call it a bolted fault also. There are the different types of the faults: two-phase fault, single-phase fault, phase-to-phase faults, the ground circuit, and the current tremendously increase, damaging your equipment. So you have to take care of that and immediate shut of the power lines, protection, operation of the power system to be ensured within minimum time. I told you that should be not more than 0.07 second in low voltage lines, and in HT it will be different timings. The three-phase fault, clear of earth and three-phase fault to earth are balanced, are symmetrical short circuit fault, while other remaining faults are unsymmetrical faults. This may be due to internal external effects. Internal effects include breakdown of transmission line, equipment, aging of insulation, deterioration of insulation in generator, transformers and other electrical equipment. External effects include overloading the equipment, insulation failure due to the lighting, and so on. Arcing faults can lead to fire and explosion in equipment such as transformers and circuit breakers. Abnormal current causes the equipment to get overheated, which further leads to reduction of the lifespan of their insulation. The operating voltage of the system can go below or above their acceptance value that creates harmful effect to the service rendered by the power system. The power flow is severely restricted or even completely blocked if the short circuit fault persists. Line to ground. A single line to ground fault is one of the most common faults, and experience shows that 70 to 80% of the faults that occur in power system are of this type. This forms a short circuit path between the line and the ground. These are very less severe faults compared to other faults. In certain special cases of phase to neutral fault, the zero sequence impedance of the source is less than ZSC. For example, at the terminal of star zigzag connected transformer or of a generator under sub-transit condition, in this case, the phase to neutral fault current may be greater than that of a three-phase fault. A line-to-line fault occurs when a line conductor, other line conductor, heavy winds are the major cause of this fault, during which swinging of the overhead conductors may touch together. These are less over fault and its occurrence range may be between 15 to 20%. Line to line, this is the most fault. Two lines come into the contact with each other as well as with ground. These are severe faults and the occurrence of these faults is about 10% when compared to the total system faults. Unsymmetrical faults are analyzed using methods of unsymmetrical components in order to determine the voltage and currents in all parts of the system. This analysis of these faults is more difficult compared to symmetrical fault. This analysis is necessary for determining the size of the circuit breaker. For largest short circuit current, the greater current usually occurs for either line to ground or line to line faults. When the fault occurs in any part of the system, it must be cleared in a very short period in order to avoid greater damage to equipment and personnel, and also to avoid. At that time is normally taken as 0.1 or 0.2 second. So you have to be very careful at the location of the fault, the amount, the quantity of the fault current and your protection system. Their time inverse curve will determine their protection timings. The fault clearing system uses various protection devices such as relays and circuit breaker to detect and clear the fault. So your protection depends on clearance of fault in a way that's possible shortest time. The protection can only be designed if we know about the amount of current which will flow. For that we need to calculate the short circuit current. You can see over here in this diagram, this is the flow of the current in a short circuit current, and the peak value occurs in the first cycle. And when a steady state condition comes in and a DC component RMS value of a DC current also comes in, I will simplify all these things with a simple calculation how to calculate this short circuit amount of this short circuit current so that you can select your protection system accordingly. My utility system, they don't consider that. In industrial plants, they don't consider that the system capacity short circuit current. This is called the fault current or fault zones. So you have to be very careful when you're selecting the components and designing a system. Either in a maintenance network also, you need to correct accordingly. So this is a cycle which and the first thing is that for the protection system and minimize the breakdown, we have to take into consideration the sub-transient reactance of the system. And your basic purpose is that your fault should be removed within the first cycle. So that is very important to minimize the damage. So this is the decaying component, the same in that case, sine wave and how they behave, X by R ratio significance. Short circuit analysis is a critical piece of the engineering study for a power system. This analysis determines the maximum available fault current in the system, hence the maximum level that the electrical equipment should be able to withstand. When a short circuit occurs, the total short circuit current consists of AC components, as I shown in the diagram, varies sinusoidally with the time, also known as symmetrical current. DC component non-periodic and decaying exponentially with the time constant of L by R. L by R is the proportional to X by R ratio. The DC component makes the symmetrical current become asymmetrical. The X by A ratio affects the DC component, therefore also the total current. The higher the X by ratio of the circuit, the longer the DC component will take to decay, longer time constant. So you have to minimize the X by R ratio. Now, we come some sort of the practical calculation. Now, there is simple calculation. You just have to remember the Ohm's law and calculate the impedances. So, first of all, you have to remember this thing. The source of the fault current is only the dynamic machines. Dynamic machine may be the synchronous generators, synchronous motors and condensers, induction machines, and electrical utility system can participate in that, contribute in your short circuit current. And the motor becomes a dynamic contributor to the short circuit current. When it trips, it will come at the few cycles, the opening cycle, it will come as a generator, act like a generator because of the inertia of the motor. So the motor will contribute as a dynamic machine to the total system short circuit current. So you have to remember that the motor contribution can also be considered in total calculation. If you are in a plant a lot of motors, there are certain assumptions also, lot of things. I will just tell you about that. And the, I have taken it from the Siemens handbooks and Schneider handbooks and that sort of the things. So first of all, you have to make your mind. The transformer will not contribute into short circuit current. Transformer will not contribute into short circuit current. The every dynamic machine will contribute into I will just step by step. So there are different methods. So now XD double dash is the sub-transient reactance determined current during the first cycle. And this is our main purpose. You have to operate your protecting device in the first cycle to minimize your losses, damages. Transient reactance assumed to determine the current after several cycles, and synchronous reactance, this is the value that determines the current flow after steady. So our purpose, the sub-transient reactance, either you have to assume it or the component vendor will give you the sub-transient reactance of your component, maybe generator and so on. Generator synchronous reactance is seldom used in calculating fault current for application of the device like circuit breakers and fuses. This I have explained it to you. A simple method. No difficulty in that. Ohm's law, use of the Ohm's law. Let's come to the actual calculation. You will see over there. These are the different formulas for conversion of. You have to formula three-phase system where the base voltage is the line to line voltage in volts of kilowatt, and the base apparent power is the three-phase apparent power in kilowatt, ampere or megawatt amperes. So these are the different formulas application of this. So what happens that you have to select the base voltage and convert your all impedance, reactance and resistance to this base voltage and calculate as per Ohm's law your values, short circuit current. So these are the different applications of the different formulas, not difficult. If you go for academic, in your academic, you have seen you have to calculate the positive sequence, zero sequence, and negative sequence current. We have avoided that, and so a lot of assumptions are made. So to simplify, to calculate the short circuit current. So in per unit method, you have to select the base value and convert all your impedances to this value. This is the per unit method as per I see the most useful and actually useful and easiness. It will have the easiness of all that thing, and you can calculate Z per unit. So we will give you a practical examples, and we'll come to that and solve that with the ETAP method also. And you can go for Ecodel also software also, Schneider software. For that you can easily calculate all that sort of the things. The XPU, your basic purpose will be XPU per minute reactance base kVA upon kVA rating. So maybe in a plant, you can understand that you have a different source of supplies. All that data has to be converted into XPU. And normally, generally, assuming that the resistance is neglected, so XPU, the reactance per unit method. Now, the procedure you have to adopt manually. At present, we are discussing about the manual. Prepare system diagram. This is called the single line diagrams. Collect and convert impedance data. You have to calculate the resistance and reactance. Then, according to series parallel formulas, you have to get an equivalent impedance of all these circuits. Just like in your academic or in your practical field, you solve your electrical circuits. This is the same thing. No problem in that. Combine impedance in series and parallel, and then calculate the short circuit current by using your Ohm's law. A one line diagram of the system should be prepared to show all source which is called the SLDs or single line diagram, current and significant circuit elements. So you will see impedance data should be collected for important and converted to per unit on basis of selected for the study. So these are the conversion. You know that star to delta, how to convert star to delta for combining the impedances and delta to star. So this is the simple solution for that. Now let me move a little forward. So I will just explain you this per unit method taken from a Siemens handbook, and it will give. This is a simple complication. Let either we go for that. The fault these are the different formulas, and assumption for HT side is considered to be negligible small. ISC will be IN into 100 upon USC. For several terms, ISC is added. So ISC at any point in LV system, ISC, you can calculate by this formula. R3, X3, equivalent impedance of HT network. Normally, the HT network, the fault level is considered minimum at 250 MVA and the maximum at 500 MVA. This resistance reactance is over there. Source of impedance for utility. This is the formula for that PSA fault level in kVA. These are the different formulas. You can take it. I will just omit that so you don't want to confuse yourself. This is the single line diagram. This is called their ceremony methods in calculating the short circuit currents. The point to point method normally used in USA. Impedance method normally used in Europe. And percentage impedance method or impedance method are the same thing. And then you have to just per unit method. And there is one more which is called the short KVA method, which minimize the calculation for that. There will be little difference between 4 to 5% in the actual calculation, but that is also useful for that. You go for that, you can do it that. So this is an impedance method, different formulas over there. The assumptions are in that. This I have taken from a Schneider electrical installation handbook. It's very well explained over here. This is you can see you have made a single line diagram and different you have calculated R and X resistance and reactance. So R is taken as 15%. R can be therefore be neglected in comparison with X. Transformer figure is the PCU is the transformer losses into 10 raised over 3, 3 into rated current IN. So circuit breaker we have taken as negligible, bus bar negligible. You have to take R is equal to rho into L by S. You know that. This is the standard formula for that. Circuit conductors, you can calculate the R resistance over there. Three phase short circuit current K, you can take the different ISC as per Ohm's law. This is the simple thing. And the salt example over there, you can see over there. I all have calculated like this thing. And you go into details of this thing, you will very well calculate yourself how what will be the short circuit on each bus pass. At what location, up to what impedance we have to calculate, you give you your short circuit current. This is one method which shorten your calculation, the short KVA method. And I have taken an example of 11 kVA to 50 MVA, 1500 kVA with a voltage impedance of 5.75%. There are four motors over there. Now, I have told earlier that the transformers 200 horsepower. The transformer, these motors contribute in the short circuit currents. So you have to assume in the sub-transient reactors. I will just show you when the fault occurs. I have taken the fault at the bus pass. So all these four motors will contribute some short circuit current because they will become the source of current. And when the fault occurs, and the utility will also contribute. In short KVA method is very simple. Short KVA method, as sub-transient reactors of motor is assumed to be 0.17, and it is allowed 1 horsepower will be taken at 1 kVA. Therefore, the total short circuit power available at utility supply 250 MVA is 250 MVA, and motors are 200 horsepower, 800 we taken at kVA. So the motors contribution be 4705 kVA, and 250 MVA of the utility will come 254705 kVA. Power attenuation provided by transformer let through current. We call that transformer the let through current. This is the maximum fault current which can pass through the transformer. And this depends on the voltage impedance of the transformer. So this is 26086. In this method, that one also is reciprocal of the sum of the two. Now you can take it as the short circuit current with a simple calculation 34K, and you will collect your components accordingly. The nearest to 34K are above 34K, not less than 34K. This is another example, practical example, which I told you that capacitor do not contribute fault KVA. Resistive, same is same example is there. Resistive load do not contribute fault KVA. VFD do not contribute fault KVA due to not containing regenerative character. Cable impedance are neglected in this case. So you can make a lot of assumptions over there. So you can see over there. This is also calculated in the same way. And for generators, we take the sub-transient as to 15%, and motor is assumed to be a 17% in this method. So utility fault level is taken at, in this example, 350 MVA. Whereas in Pakistan, you can have 350 to 500 MVA fault level of the utility company. Start down circuit and you can calculate it, because in the KVA method, the series are reciprocal and parallel are added, and you can calculate this currents accordingly. So this is a step 3. Utility contribution is step above the arrow, and the motor contribution is also contributed to down the arrow. And this will give you the total fault current about 24,590 kVA, and you can calculate with the help of the kVA, you can current your short circuit current and select your components. Now, this we come to the bi-unit method, and in this example, you will be a little confused because we will calculate the resistance and reactance. Simple application of the formula, nothing else. So we have a motors of 100 horsepower and sub-transient reactance of 25% we have taken over here. Or base power is assumed to be per unit method will be, you will select a base value. So the maximum power transformer is taken as a base value. This is a 1000 kVA in this example. So base current is calculated is equal to 1443 IB. Base impedance is calculated 0.162 as per formula. 11 kV source impedance is calculated 0.000287. Contribution from 11 kV network is 350 MVA. We assume utility contribution is 350 MVA. So therefore total impedance is calculated as 0.00019. X is 15%, R is 15, and you can take transformer impedance and dividing it 5.75, and RT and XT waveguide impact of the cable is also taken in that, and this comes out to be 0.054 ohms per 1000 meter. According to your distance, you can proportionate this to find out the real resistance and reactances. Motor contribution 1 horsepower is equal to 1 kVA, X by A ratio is equal to 6. Total number of motors is 400 horsepower. Average sub-present reactance is 25%. We have assumed it. And R is equal to 1.467. So base kVA, R and X we have calculated. Now you can draw a diagram, resistance and reactance. Then separate them, this resistance and separate circuit and reactance in a separate circuit. So you can see over there, we have calculated the resistance diagram and find out the total resistance. Now this is the reactance diagram. The parallels are as per series parallel system. Reactance diagram and the resistance diagram we have calculated, and the total resistance R is equal to R square plus X square. So you can have Z value which is equal to 0.0570, and the RM you can take it base ampere of a per unit Z is 25 kVA. Now, this is more easiest method in fault calculation with per unit method. It is also an application of the same thing, nothing else, the same problem. So, what you do, this is from the Siemens handbook, select common kVA base for all calculation. This is usually the most common transformer kVA rating in the system at some convenient base such as 1000 kVA or 10,000 kVA. The formula is, I will explain different formulas. This is the application of the simple formula. Common kVA base upon kVA base. We have taken this. Change impedance values to per unit values on a single common kVA base as selected in step 1. Change fault levels and capacities to per unit value on the common kVA base. Now there is a solution of the problem as per the formulas, given formulas. Change motor horsepower rating to equivalent kVA. Determine motor feedback contribution to short circuit kVA. Convert single line diagram to an impedance diagram with all impedance values identified. Reduce impedance diagrams by combining impedance using short circuit arithmetic method. Rigorous approach involves factor combination using actual values of reactance and resistance. Calculate RMS symmetrical short circuit. It's simple. So you can see these are the different formulas and assumptions. You can have it over here. Now let's come to the actual solution. I have intentionally put same 480 where I copied up at this thing so that you can recalculate it as per your 400 volt, 15 volt with the Pakistani system voltage. So this is a transformer of 1500 kVA. Z is equal to 5 voltage impedance is 5.75, and voltage you can recalculate. You have to take like pencil and a copy, and you can have to calculate. So for the fault is at the bus bar level. So feeder 1, feeder 2, feeder 3, feeder 4. In calculation, you that kVA base is equal to 1500. We have selected it. Utility supply per unit impedance kVA base upon kVA short circuit, which is taken in this system is 250 MVA. So this comes out to 0.006. Transformer per unit impedance is 5.75 divided by 100, 0.0675. And if you go for this thing, you can see over here, a simple diagram is derived over here, which will give you the utility supply, transformer and fault. Then the rest of the feeder, motor contribution and cables impedance will take part. These are the 4 feeders. And their utility, you have calculated all these things in this thing. So you can see over here 0.06 is written over here as 0.06 and 0.575 fault. These are combined to 0.635. Similarly, for the motors, we have calculated motor feedback kVA based upon 4 into motor kVA. The motor kVA, we have 200 horsepower motor, it comes to 200 kVA. So each motor will contribute 1.875 per unit. And cable impedance Z ohms into kVA base upon 1000 to kVA square. So you can calculate according to this formula. This comes out to it is 0326. So now if you put these values over here, 1.879 and 0.326, then series add them and then take out 1 upon RT is equal to 1 upon equivalent values, you can calculate it, then calculate the short circuit current. ISC, I am a symmetrical current KV based upon ZPU on this comes out to be 32 KA, 32 or 33 KA. And the next fault level, if the breaker is off, breaker is on and the short circuit occurs in the second fault, it comes out to be 28 day. We have assumed that the breaker is not tripped and the next fault will be at the motor feeder, one of the feeder, and it will give you a different reading, and you will take the three feeders also. So these are the something which will give you a little awareness, need your practice. You have to apply your practice and practice all this manually, then apply the software application. So my colleague Mr. Saifullah Baloch will just give you the simple software applications on ETAP. It's very easy. Whatever we have calculated manually will be a little complex and you can see over there. If you can use Equadel software, go to the goggles, download 4.8 version of the software, Equadel, which is based on ETAP and developed by Schneider, France. And that's also very easy. Either ETAP, which is most famous. So we give you a little demonstration on ETAP. Thanks a lot.
Hello everyone. Now I'm going to start a software application for calculation of short circuit current in case of any fault. So fault can be many various types as sir have already explained. So let's move for the software application. So firstly, I would like to give you some introduction regarding the ETAP 19.0.1. It's one of the most famous software used for the electrical drawing, electrical parameter analysis like short circuit, arc flash analysis, and load flow analysis. So here you can also have two options: the AC short circuit, AC arc flash, AC load flow, and with that same you have these option in DC also. So today we are going to calculate the short circuit. So here you can see the interface of this software. First, when you are in edit mode, you can add these components in this for making this single line diagram. We have already built an single line diagram of having a utility supply, having an short circuit MVA of 250 with a transformer of 1500 kVA. Along with that, we have a circuit breaker, that is main circuit breaker CB1, and with that we have a bus bar. The bus bar 19, that is of 0.415 kilovolt, that is according to Pakistani standard 415 volts. So this is available in the three phase voltage, that is line to line voltage. Now here we have connected the four branch circuit having a motor of 200 horsepower on each with a circuit breaker connected to it, and we have also notified here bus bar for putting a fault as a case of example. So let me go to in a short circuit mode. Now here you can see on this tab there are different modes available. Here you can see I have just got my cursor on short circuit. You can see that there is a brief introduction regarding that short circuit switch the current presentation to short circuit analysis mode. So here we click this and we are going we have just about to start our short circuit. Now for a short circuit you need to have a fault on some electrical, you can say, component or any branch circuit or anywhere you want to put. So if we are taking as an example that if we generate a fault on this bus bar, then you have to right click on it, and here you can see there is a checkbox, and what it says a fault. So if you check this box here, if you just click on this, you will see a green tick that comes in it. So this bus bar has now a fault. Now for the fault, there are 3 to 4 types. You can select here from this display. Now what kind of fault you want to put? That is three-phase fault. Now let me just start by this. Run a three-phase device duty na. So here you can start the three-phase fault and you can calculate the parameters. Now just look at it, that we are having a current contribution of 1.246 kilo ampere from this main supply. Here you can see the arrow is showing and it is downwards. It means the current is coming from the utility supply to the branch circuit or the main bus bar. Now from the transformer, as we know, the transformer transforms the higher voltage lower voltage level to higher voltage, or lower voltage level higher voltage level to lower voltage. Here we have used a step of transformer, which step down transformer, which step down the 11 kV kilovolt uh, 11 kilovolt supply to 415 volt on the secondary. Now since the voltage has been transformed from higher value to lower value, so it will cause the current to increase. Now as you can see, from this transformer and through this circuit breaker, we are getting a current of 33.023 kiloampere, that we can say around about 33 kiloampere is contributed from this line, from this transformer. And as sir have already told, that the motors which are running on a branch circuit, they also contribute to a short circuit because of their inertial generation. Like inertial generation, we can refer as that, for example, when any fault occurs and the motor was already running. So in this case, what happens? The voltage at the motors, if the fault is not at the motor and before the motor, the voltage at the motor will be eliminated, it will be removed, so motor will stop. But before stopping, it has an inertia and it will keep moving until it stops due to friction. So while that running, while that last for a short time run, at the end it will contribute a current, and that contribution of the current depends upon the current power rating of that motor, that how much power that motor draws when it's running on its full load. So here we have a motor of 200 horsepower, so it will, as it has an high power rating, so it will contribute a current of higher rating. So here we can see that 1.325 kiloampere of current is contributed by each motor. So uh, this branch has two side contribution, one from the transformer side and second is from the motor side. So from the motors we have four motors, so they will each will contribute, and this bus bar will have a total short circuit current of, you can see, let me show it to you. So this bus bar will contain 38.315 kiloampere, that is 38,000 ampere of short circuit this bus bar will be carrying in case of fault. Now here in the ETAP we have different options. Like if you want to see the maximum short circuit current, you can just come over this side, on your right side you can see run three phase uh, run three phase, line to ground, double line to ground, and here you can see in the bracket there is an term used, that 1 by 2, and that is half cycle. So for as we all know, and sir has also mentioned is in his presentation, that a short circuit has a maximum value in its half cycle, and this half cycle is the highest current in the half cycle, and the first half cycle is because of the sub-transient reactance, because it is responsible for the maximum short circuit. So if we run our short circuit on this one, this option, you can see that a highest short circuit current that we are getting is same as we have just noticed in the duty cycle, that is 38.315, because in the duty cycle it also shows its maximum short circuit current. Now let us find the one current from half cycle to sorry 1.5 cycle to 4 cycle, that what amount of current we will be getting through this. Now here you can see we are getting 35.138 kiloampere of current. So it is bit less than the maximum current, because when a short circuit starts, it depends upon the sub-transient reactance, and it has a maximum value. Then after that half cycle, it start to decrease, and it then depends upon the transient reactance. Then it goes to steady state condition. Now for the minimum current, you can go for this option. Here you can see MIN, that is minimum, a short term used for minimum short circuit current. You can see we are getting a current of 33.03 kiloampere, and this terminology, this term which we are getting over here, that is actually 81.54 degrees. That is the angle. Okay, that is the angle. And now you can also see here the bus bar. Here it shows 0 kiloampere, 0 degree. You don't need to get confused, because at the minimum, at the 30th cycle, as I've told you, that motor will contribute its current just for a few, you can say, seconds, due to its inertia. But till then, if the current has reached at its 30th cycle, the motor has already would have stopped, and it will not contribute current toward the main bus bar. So you don't need to get confused that because of this zero at this current rating at this bus bar. Na? So only the current which we will be getting, that is from the utility supply, that will be 33,000 kiloampere, having an angle of minus 81 degrees. Now you have different display options for that, that what kind of fault you want to generate, what kind of fault you want to inject, and what kind of parameter you want to see at the bus bar in the case of short circuit. So here you can click on the display options, and you will find the voltage unit. You can change it from the percentage to kilovolt. You can also see the fault type, and you can also easily change it. For example, let me take an example, that now we have parameters according to three phase voltage fault, and that is the symmetrical fault. Now if we change this to single line to ground fault, it will have different now options here, that VB, or displays the phase A voltage and zero sequence voltage. Okay, zero sequence current. Now for if you want to see the sequence value 120, and if you want to see the phase values, you have different options now. Now we are just putting here the phase A voltage and the zero sequence current. Na? And for this display load contribution, medium voltage motors, large voltage, or static load types of voltage loads. Now you can also change that whether you want to see the contribution of the loads in the short circuit or not. If we remove here the medium low, medium large or small low voltage motors, then we can we'll be experiencing a lower value even in the maximum short circuit fault, because we have eliminated the load contribution from this display, from these display options. Now if you just change the tab, here you can also change the different display options. If you want to add that, you need to show the node, circuit breaker, fuse, switch, and you need to just go for the ID rating, kilovolt, or you want to see the phases, different one. Okay, AC to DC, if you have a conversion, you can also see colors, you can change from here. So this is just because of your, you can say, easiness and convenience, that you can easily see the different display options. Now we have just started here the line to ground fault, and if you want to change, if you want to see the maximum current fault, you can see here that at the time of three phase fault, we were getting an amount of 38 kiloampere, and now we are getting 37.68 kiloampere of short circuit current at the line to ground voltage. This is because we have not selected the three phase voltage fault. With in that place, we have just went for the line to ground fault. And most of you can ask that this type of fault has a lower value than the other types of fault. Let me clear a thing that whenever line to ground fault occurs, it can have maximum value, or you can say the more value than the three phase fault even, just because of the difference of zero sequence impedance and short circuit impedance. If your source impedance and short circuit impedance, if your short circuit impedance is lower than the source impedance, then your line to ground fault will be more than the three phase bolted fault. So this is according to IEC 61364, that is mentioned in the Schneider book, electrical installation. You can say the book title is electrical installation. You can go through it and you can find that why this line to ground fault has a maximum value just because of impedances. You can also find the reason behind that. Now, here let me take another example, a short example. Then you can try by yourself that how you can change the different. You can see that from where the fault is. You can say you can generate, or you can inject. Let me just first you have to remove the fault from this bus. For example, if you want to now put a fault over this bus at bus 31 at the fourth motor. Okay, now this bus is faulted, and by this color you can also see that it has become now red. So you can easily find out that which bus is faulted now. Now we have started the maximum current. Now let me change it to three-phase fault. Okay, now we have changed it to three-phase fault. Now here you can see that 33 kiloampere is coming from the main utility one, and 1.325 kiloampere current we are getting from these three motors. But this motor is also contributing because the inertia has not, you can say the inertia is still present in this motor at its half cycle, start of the half cycle of the short circuit, and the total current at this bus bar is same as the main bus bar, 38.315, due to the contribution of these four motors. Okay, so this was how you can inject a fault and see the parameters, the short circuit value for any kind of single line diagram at any industry or whatsoever. Thank you very much. If you have any
So
question.
the just announcement is that we have mentioned that ECAP and Equidel.
Okay, correct.
So if you want to know something about the Equidel, we have conducted our engineer Mr. Zadi has conducted it. We can send it to you on your request.
Okay.
If you are using an Equidel Schneider software 4x8 version.
Yeah.
So that is also very practical. So this is the ETAP demonstration. And Equidel webinar, if you request it, we can send it to you. So that we can use of both the and
Okay.
both will give you the same short circuit as well as any other parameter.
Okay, so for your more knowledge, we have just want to inform. We are just going to inform you that we have another webinar already. We have done that by a few months back by our project engineer Muhammad Ali Zadi, Muhammad Zadi. So you can also go through it, and if you want to just see recording, and you can request it, and we can email it to you, or you can also use the yeah, we have on YouTube. Yeah, that is also available on YouTube. You can go through, go to it and check it out and watch that video. That will be helpful for you, na? So that is about the Ecodal. That is software. Na? Sir has also mentioned about that. That is about the Ecodial, and Ecodial is also an electrical software used for such single line diagrams and for different simulations, and you can go through this webinar. That will be more helpful for you. Thank you very much. If you have any question you can ask. Breaker and SLD. Mr. Heather Habib, yeah, we have added the circuit breaker in the SLD. The boxes, they were actually showing you the circuit breaker that were present at that side, at the main bus bar, and also there were circuit breakers in each branch circuit. Any question? What happens in the case of multiple transformer in parallel? So multiple transformer in parallel, it's actually depending upon your load. If your load is
The
exceeding
multiple
the
transformers,
Mhm.
all the short circuit of each transformer will be added.
Yeah.
T1, T2 plus T3, the total short circuit will be collection of all this
Yeah.
on the bus bars.
Okay. So in the case of parallel transformer, actually initially it depends upon your load. If your load is exceeding, then the kVA rating of the transformer, then you can add the parallel transformer, and it will also contribute in the short circuit. But it
Not contribute. Transformer will
no,
allow let through current.
lead through short
Let
circuit.
through short circuit.
Yeah, it's not a source of short circuit, but it's a lead through one, it's a channel. Can you provide ETAP training? What will be the duration of ETAP training?
One day.
Gentlemen,
One day.
if you want to learn ETAP for different purpose, it depends upon the number of modules you want to learn. So on YouTube you can find different tutorials for it, and even on the ETAP website itself you can find there. And if you want to learn it, you can contact me personally. Here
One
is
day.
my email.
I contact UES.
Personal phone.
UES. UES.
Okay.
मेरा
This is my email. You can check it out.
मेरा भी email डाल
Okay, can you enlist some of the benefits of fault analysis instead of designing phase? Okay, fault analysis, as sir have already clarified this thing, that because you want to design your protection system, and for the protection system you need to you need to install the protection components like circuit breaker, relays, different other protection schemes you have to design. So for that you need to initially analyze different faults, that how much current you will be getting, and what will be the position of that of that amount of current. So it depends, because of this different you can say parameters that you have to that are required. So you need to first have fault analysis, and then you can design your
if
protection
you are
scheme.
in maintenance,
Hmm.
then vetting of the all your circuits will be done with this help.
Mhm.
You can improve your safety compliance
Yeah.
as per fault analysis.
Yeah.
Maybe the designer have done something wrong.
Okay. Yeah, Kamal, you want to say something? In operations, if you want to have a reliable operation, the continuity, you want to ensure the continuity,
Select protection,
you have
selection
to,
of the component
yeah, you have to select the best protection scheme for your design, for your
as per
system.
your fault location.
Yeah, and for that you need to have fault analysis. And remember that current you can't estimate the complete fault analysis just by analyzing analysis of a single point. No, you have to go through the whole system, and position of each you can say fault differs the current amount of current. So you need to design
Let
the
me
system.
add something more.
Yeah.
In the utility company, in the last rains, so about 200 people died. So all this are because of the
Poor fault analysis.
poor fault analysis.
Yeah.
If the utility company do some, the cost will be saved and the real protection will be done. The
Yeah.
purpose of all this component selection is the protection of the equipment, human being and the equipment.
Yeah.
And if you don't do your fault analysis, your component selection will be wrong. Yeah. And no tripping mechanism will operate.
Yeah, sure. So this is the reason that why we are conducting fault analysis. Okay. Another query or question you guys want to uh, write it down or just ask?
Just email at us, we will then.
Yeah,
So
if you have another
have any
query
other problem,
later on, you can just email us on our official email address, or you have also my personal email address. You can also email me there, and anyone want to learn it, they can also ask for that one. Okay.
we will also learn something from you.
Thank you very much. Okay, so thank you very much for joining us today, and inshallah we will be having different webinars in coming days. Okay, what is the PF effect in ETAP on short circuit calculation? PF effect, power factor.
Power factor effect.
No, but power factor effect, no, it will not affect. Power factor, it's a parameter, it depends upon your load and your, you can say, character of the load. Either is a reactive, either is a you can say reactive or resistive. So it depends upon the nature of the load. So it will not affect the power factor.
The power factor will not change the impedance of the loop.
Yeah, it will not
So
change.
the short circuit current depends upon the fault loop impedance.
Yeah, fault loop impedance as well as the sub-transient reactance. That thing you have to keep in your mind, that higher the X by R ratio, that is the reactance to resistance ratio, higher will be the duration of the short circuit current in its first cycle. Na? So you have to keep this thing in your mind. PF actually is a parameter that is calculated after the load connection. Na? When you are running a load, and this is also a point in short circuit, we have also you can say an amount of power factor that we that is mentioned, that will be mentioned at the PF meter or something else, any component which is dedicated to power factor. So that depends upon your load. Okay, and in case of short circuit we will be getting very low power factor. Okay, I think now we need to end it.
If you know question, then if you have any question, please call us
Please
or mail us.
mail us. Yeah.
We will help you.
Okay, 1 minute with me and
Thank you.
take it. Okay, so at the last, you can email us for any query or any help. Thank you very much. On higher voltage like 16 short circuit available down. On higher voltages like 690, the short circuit levels will be down. The 690 volt, that is kilovolt or volt. If it's for example
Yes, wind turbine. These are the voltage from the wind turbines.
690
690
volt,
voltage is the wind turbine.
wind turbine standard voltage.
Wind standard voltage.
Okay, so it will increase the short circuit level
Yes.
or not? He's asking that.
Maybe if the source is more, then the short circuit will increase. All depends on the impedance.
All, yeah, it depends upon the impedance also, and yeah, voltage also
Either it is low
contributes.
voltage or high voltage.
High
The
voltage,
short circuit also depends on the loop impedance.
yeah, impedance, and it also depends upon the utility short
Short
circuit
circuit level.
short
The
circuit level.
11 can be short circuit level is 350 to 500 MV.
Yeah, 500, and if you increase the rated, if you are having a utility of higher voltage than the 11 kilovolt, you can also have higher current. Okay, so can we trace any fault with the help of ETAP during the operation? During the operation, you cannot trace it. You have to inject the fault.
Yes.
Yeah.
You have to select the fault at
Yeah.
certain location
Yeah.
and find out the short circuit current and then check your components
Yeah, this is the
accordingly.
analysis.
Yes.
Yeah, this is the analysis. You have to assume that if the fault is occurring on the bus 1 or bus 2 or at motor circuit or generator
Our
circuit, whatever.
experience is that the utility companies, even industrial sector, are selecting the wrong component, not as per their fault levels.
Yeah, fault level. So you have to assume at different places on your you can say
And put your
system.
components accordingly
Yeah,
so
then
that your safety compliance will be done.
yeah, then you can able to select your components accordingly.